Welcome back, everyone. We are back to our session. So right now we have our next speaker, Dr. Christopher Petersen from Air Force Research Lab, Space Vehicles Directory. And he will be talking about towards hybrid model predictive control for computationally aware satellite applications. All yours, Chris. If you can unmute yourself, excellent.
Yep, sound check. Can you hear me?
Yes, very well.
Fantastic. So thank you, Ricardo, and thank you all for attending this workshop. There's been quite an astounding amount of material as it pertains to computationally aware algorithms, especially in the regime of model predictive control. And today I'll be talking about hybrid model predictive control in applications to satellites. And this work is in collaboration with my colleague, Dr. Sean Phillips, who works with me at AFRL Space Force, as well as Don Husdick-Schultz and Ricardo from University of California, Santa Cruz. So to begin, just kind of a little bit of an outline here of what I'll be talking about today, and a couple of snapshots of pictures that you'll see that kind of go through the presentation. I'll give a little bit of motivation behind why model predictive control is useful for us for satellites, as well as some of the computational complexities that aren't really seen on other platforms or vehicles. Then I'll introduce the community a little bit to what we do for satellite modeling, as well as how it pertains to problems that are of interest to us here at AFRL. I'll talk about our model predictive control kind of framework, but I don't think I need to go too much into depth considering the wealth of knowledge of this community. And then I'll talk about our hybrid model predictive control formulation and how that starts to add into how we see the problem and how we can start getting a holistic analysis, fusing not only computation, but control methodologies. Then kind of wrapping it up with a future experiments as well as lab facilities. And then I'll open the floor to discussions, not only with just myself, but also with my research colleagues that are on this workshop call. So going into a little bit about the uniqueness of where satellite applications really start seeing a lot of computational burden is if you look at the state-of-the-art processors that are used for satellite vehicles, the example that we use here is a RAD 750. Really, we have a 200 megahertz max clock rate, and really this memory total there is really looking at 64 kilobytes. And if you look at the new iPhone, really the processor and memory load for that is by far orders of magnitude greater than what we would ever get on orbit. And not only that, but if you look at the price range, for satellite processors can range around about $200K, whereas for the iPhone, you can get it around $431. But why is there such a lag in this computation? And really it pertains to radiation hardening. So when we deploy satellites, because they are in an environment where we consistently see radiation from the sun or other gravitational sources, really this can start to disrupt, degrade, or destroy electronic systems. So what that has impact on us is that we can see data corruption, which, for example, can lead to bit flips, which can ultimately lead to a satellite producing false information, which can also cause the satellite to reboot, which is not beneficial to us in the least bit. Radiation can also harm circuits, which can totally ruin our satellite on orbit, as well as make it inoperable. And onto that, as well as memory loss. So if there's particular data that we are of interest, if it gets hit by radiation, we have the potential of losing that. So all of this leads to the aspect of that all of our computational processors have to be radiation hardened, which really creates a 10 to 15 year lag on our processors versus what you might see on Earth. Now, in order to combat this, there are three major options we can do. We can develop operational satellites on a shorter time horizon. Some of you might have seen recent literature that are using processors like Raspberry Pis for satellites in low Earth orbit. Those satellites really have a lifetime of around 6 months, and so that's fine. But for operations that are of particular concern to myself, we look on operations on the order of 1 to 5 to 10 years. And so we can't really have a processor that will die out on us within 6 months. And that gets to the second aspect of put terrestrial processors in a lead box. But really what that ends up being is it creates a whole size, weight, and power aspect to things, which really becomes very cumbersome as we start to design our other payloads. And the option that we actually start looking at in this presentation is how do we develop algorithms that we can adjust the computational load of the processor? So can we design an algorithm with parameters that really we have a keen idea how that impacts our computational load? And that's not just in terms of computation time, but also processor load, memory load, et cetera, et cetera. So getting into our solution, like I said, is developing algorithms that can adjust to computational loads, which is really unique for us. And to highlight at least a couple of the aspects which are useful for satellites is we are operating in an unknown environment that requires an adaptive control methodology, which is why MPC is so attractive to us. We toss something up into orbit and it's not like we can see it with the naked eye. We have to trust that it is operating in this sort of unknown regime. And in addition, satellite operations require fuel optimal solutions. Always when we compute a control trajectory, fuel is of priority because there are no gas stations in space yet. I really hope that changes probably within the next 5 to 10 years. And we've heard a lot of talk about safety, and that certainly is of concern to us in the satellite regime. If you are familiar with a couple of years ago, there were 2 satellites, one Russian and one US, that collided, created about on the order of 5,000 orbital debris, which still causes us headache to this day. And we need algorithms that are computationally efficient. This is because that while we here think that GNC is the most important thing in the world, that's not the primary mission to other satellite operators. They have their own missions that pertain to satellite observations or basically sensor measurements. So we need to make sure our GNC algorithms are not the primary reason why our board is being computationally loaded. So the technique that we look at is model predictive control, and it's useful because it provides a way of computing an ever-changing optimal control path, which enforces safety. And what we do in this hybrid model predictive control framework is really starting to look at solver dynamics. We look at underneath the hood and understand how the solver actually gets to the solution and see if we can account for those dynamics as we start wrapping it into the overall framework, which allows for the creation of a technique that gives a balance between computation and optimality and allows for us to actually start integrating it into our whole satellite process earlier than normal. And so to give a nice little framework of typical models that we really start looking at in the satellite regime, I'll be going over right now the Hills model, which if you're familiar with, it's a linear dynamical model. And so satellite motion is inherently nonlinear. The equation that you see of r double dot is equal to basically negative mu over r cubed minus 1 over m times u. That's inherently nonlinear and produces orbits that are closed, periodic, and elliptical. But if we start looking at 2 satellites moving in proximity to one another, probably on the order of 500 kilometers or less, that motion can actually be simplified into a set of linear dynamic equations, which you see here on the slide. And those equations have been used to quite success in satellite operations up until this point, in particular for those as it pertains to satellite swarm control. Some of you might be familiar with SpaceX's Starlink Constellation. These are the equations that they look at. They are also very useful for rendezvous and docking, especially when we start looking at how we want to do shuttle docking to the ISS, as well as in-space logistics and how we start manufacturing satellites on orbit. But the usefulness is, again, they are linear. So we can start exploiting aspects such as QP solvers or aspects that start really leveraging convexity, but those techniques start to have their advantages and disadvantages. And we don't want to simply use a black box solver. We want to understand the entire system framework. So getting a little bit into MPC, and I'm not going to spend too much time because I think everyone's aware, but basically this allows us to continually optimize over a finite horizon and really yields an ever optimal path. And so my little fun cartoon example to the right here shows that if we're trying to go from our initial location to the star, in terms of kind of moving along into the future, we enact our first control input. We assess that maybe we're off due to some unmodeled effects or due to maybe some aspect of a leaky thruster, and we recompute our trajectory. And maybe an obstacle appears in the way. We've seen those techniques this workshop as well. And so we recompute this process to get an ever-evolving optimal path. The process is systematic, which is nice. State and control constraints are handled nicely. It has a maximal basin of attraction, does not require a closed form controller, but most importantly in my mind is that we are able to have a cost function that reflects performance objectives and is optimized in a receding horizon sense. So all of these sorts of aspects really make it attractive to us in the spacecraft community. But a couple of things that we've realized as we start implementing not only just MPC, but also other controllers on orbit is, well, in particular to MPC, we measure the current state of the system, but a implementation consideration in that sort of sense is that measurements always have noise, especially if we start looking at understanding a satellite's rotation rate. The satellite measurement noise for that can be on the order of a couple degrees per second, which can lead to vastly different trajectories and can actually cause the satellite to be unsafe. In addition, for MPC, the prediction horizon is always an important concept. Longer prediction horizons tend to lead to good robustness results, but certainly increases the dimensionality and memory load if not enacted properly. And then the selection of the minimizer from the optimization solver, which depending on how much you require optimality can really lead to an increase in computation time on the order of milliseconds up to minutes for satellite operations. And apply the input in a finite amount of time. And one of the aspects for MPC literature that's kind of assumed in theory is that that the solver solves it infinitesimally fast. Now, there are some results out there in the literature that do take it into consideration in terms of a time delay, but for satellite operations, that delay can be massive, especially on the order of minutes, depending on how large the optimization process actually is. And just again, as a reminder, the formulation that we'll be looking at for this work is inherently linear, that we start considering constraints that look at aspects such as fuel constraints in terms of maximal, keep out cones, keep out zones, not just convex constraints, but non-convex constraints. And really, again, the problem for MPC is minimize a cost function subject to constraints. And an important thing to note here is that in an MPC formulation, the dynamics are essentially equality constraints. And those are added on to those safety constraints of not colliding with an obstacle, making sure you don't use all your fuel up in one maneuver, and making sure that you're not going very fast with your satellite. And I'll explain some of those constraints a little bit later in this discussion. But what I want to get into and what method that we're pursuing in this work is we actually start understanding the solver and starting to roll that into our hybrid MPC framework. So first, if we look at our typical optimal control, you'll see that we minimize the cost, which has a stage associated with a terminal, and we can formulate this into a general optimization reformulation, which basically says minimize an arbitrary cost subject to arbitrary equality constraints and inequality constraints. And this formulation is accepted by a wide variety of black box solvers. So it enables us to kind of have a one-to-one correspondence when we start testing out a variety of different computational techniques to solve the problem itself. But the methodology that we choose for this paper is to start looking at a reformulation of this in terms of a gradient descent methodology. So we look at the Lagrangian and the KKT conditions and we formulate that. And then instead of using kind of the discrete methodologies that are common in numerical methods, we actually reformulate this as a continuous time gradient flow. So if you see the equations in the lower left-hand corner here, you might see some terminology that's similar into the discrete time formulation. But why we like this continuous time formulation is because it enables a reduced memory impact over other techniques such as QP solvers and allows for an analysis via controls methodologies. And furthermore, this is, again, not an unconstrained formulation, which is typically used for this gradient flow. But you can see that we incorporate aspects of other constraints in terms of equality and inequality constraints. And knowing that we have now a dynamical system essentially that's associated with our optimization process, we can essentially view this as a two-tiered system, where the slower dynamics are our satellite model and our supposedly quicker dynamics is our optimization model. And so in this formulation, we assume that our control input is sample and hold, but what we actually end up doing is instead of assuming in the whole formulation that we converge to the optimum, we actually understand what our stopping conditions are for the actual optimization process. And we tell that the optimization should stop when the changing cost essentially converges to some sort of bound determined by some tolerance that we choose, as well as a Newton step. And when the condition is met, we assume that we're close to an optimum, although because we're acting on the KKT conditions, it's a stationary point, but we still assume that we can execute it safely. And the aspect here that's really interesting is this small tolerance here, because it is explicitly incorporated in our methodology, we can play with that as well as other optimization parameters from the full gradient flow to really start balancing computational load and optimality, depending on the scenario and mission. And what I mean by that, for example, is for avoiding an obstacle, you might need to do that operation as quickly as possible. But if you're just going to slowly rendezvous with another satellite over the course of hours, you can relax the requirements of being able to compute that solution very fast. So having these parameters rolled up in this methodology enables us to start balancing that in a way that really isn't considered in a lot of typical literature. And just as kind of the framework of how we're starting to approach this in our hybrid system framework, you can see this little flow diagram that Don had made for this presentation, where if we essentially reach our optimum, we execute it, and then the solver kind of restarts afterwards. And so this methodology really in itself is a hybrid system between two competing systems. One is the satellite system and one is the optimizer. And one of the aspects that we hope to start looking at in terms of this methodology is understanding a little bit more holistically what are the stability properties when we actually start considering computation time, computation load into the entire MPC framework, instead of just assuming that it's a time delay. How can we start playing with these parameters that enable us to really start varying it from mission to scenario? Now, just to kind of get a little bit more into the application of what we're going to start looking at, because results are still pending for how we start looking at this problem here, is the problem of particular concern is rendezvousing with another satellite while obeying safety constraints. And the particular constraints that were considered are not only the dynamics that are associated with it, the terminal zone that we get to the final location, keep out zones, i.e. debris, but we also have keep out cones because we want to make sure that our sensors are protected from certain lighting sources. We don't want to point a camera directly at the sun because that might just burn it out. And we also have constraints on max fuel limit, so you can't thrust too much, but also an interesting constraint in terms of range velocity. So you don't want your velocity to be too quick when you're close to your satellite that you're rendezvousing with. Because if you have a failure, then essentially you're going to go quickly into the other satellite and collide. But this interesting problem formulation here has a great blend of not just inequality constraints, but equality constraints, as well as those that are strictly just control constraints, state, and a blend of control and state constraints. So this problem formulation that we're hoping to look at will enable us to really start pushing the bounds and understanding the computational load for satellite problems. And in addition to that, it's not just that we're going to be implementing this in a simulation. Here at AFRL, we do have two facilities that we are hoping to leverage to start actually quantifying this. The first is called the bus replica for on-orbit systems via advanced integration, or Bonsai Lab. And this lab is essentially a 4-ton, 3 degree of freedom air-bearing platform, which has relevant spacecraft hardware on it in order for us to actually start quantifying how the impact is of this methodology. And furthermore, allows us to actually start understanding how it interacts with the actual hardware itself. And that picture right there isn't just frozen, it's actually holding it quite precisely. The second aspect, or the second lab that can be leveraged here at AFRL, is called the Robotic Orbital Control Lab, or ROC, which is a 2 degree of freedom air-bearing platform with a 7 degree of freedom arm, which starts looking at rendezvous problems when you start to get in really close in multi-body dynamics. Both of these lab facilities enable us to start looking at not just computation load, but really when you start enacting your controller, how does it start interacting with the actual physical system? And the third lab, which kind of connects them all, is called SPACER, which stands for Spacecraft Performance Analytics and Computing Environment Research. And this lab within itself has a variety of different processing boards. If you remember from the beginning of this presentation, I talked about a variety of different radiation hardened aspects. And in this lab, they have a variety of different processors, from non-radiation to semi-radiation hardened to actual radiation hardened. And so by enacting our algorithm on these boards, we'll actually be able to start seeing how the influence of parameters really start to influence our overall system. And with that, I believe I have 5 minutes left. And this is the point where I do want to open the floor to discussion, because this is really where this workshop paper is really coming into play. And I'll invite my colleagues to really start also answering questions. But some of the things that we brought up that we would like to start understanding more is, how do we model more optimization solvers used for MPC? We chose a gradient flow in this case, but we created this framework to be fairly general as well. And how do we start looking at asymptotic stability and optimality with this optimization solver when we start relieving the assumptions of you don't necessarily converge in infinite time versus you don't really converge to the exact minima? And furthermore, how do we balance computation and efficiency as well as computational certificates? So with that, I will ask for any questions.
Great, Chris, thanks for the great talk. And so we have time for questions, and we can also build from this discussion questions. So feel free to raise your hand if you have questions, suggestions. I see a lot of clapping.
Well, I will also say this too, in the sense of our lab facilities too, if people are interested in understanding more about the problems that we look at from a spacecraft community standpoint and wanting to understand leveraging kind of the expertise we have here, I'm happy to also reach out after this workshop. But at least in terms of this and the work that Ricardo and I are looking at is really starting to understand the blend between the solver and the actual problem formulation.
So I have maybe a naive question too. So is the point to be running MPC on the satellite, or is it possible to transmit data to the surface, do MPC, and then transmit the results back?
The purpose is to actually run it on the satellite itself. If you were to do it in the latter method that you proposed, you can certainly do something like that for missions that take on the order of hours to days. But for missions that require very close docking, you don't really have the time span to run MPC on the ground and relay it up. Especially, you don't want to take the risk if that information is then lost when you're beaming the MPC policy back up to the satellite.
What is the time framework for the closing the loop? Let's say if you want to close the loop by running the controller on Earth, the best case scenario, how long does it take to send the control action to satellite?
So typically, it varies in the orbit that you want. For the operations in LEO, typically it takes on the order of about a half a second to beam up that information. If you're in a geostationary orbit, which is where we start to operate most of our vehicles, that's on the order of 2 seconds. If you're starting to operate out to the moon, that takes on the order of 5 to 10, if not greater seconds. So, I mean, there's different aspects of how you want to quantify real time uh, for satellite operations, and that gets to how fast you can close the loop. But in particular, for geostationary objects, we need to make sure that if we were to close the loop with on the ground, 2 seconds is really not feasible for us, especially as we start looking at aspects of on-orbit servicing, on-orbit refueling. That time span is not good for us.
Thank you. And what is the state of the art now? Let's say, what are
Yeah.
people?
No, that's perfectly fine. State of the art, and there have been some MPC policies that have actually been utilized on orbit too. An example is a couple of years ago with the satellite Mango Tango from ESA. They ran a MPC policy that was a mixed integer linear program, but was fairly limited in that sense. State of the art at this point, if you were to run for example, if you were to run kind of a QP on a radiation hardened processor, that typically, depending on the dimensionality, can take anywhere between, I think, 10 milliseconds up to about 3 seconds. And if you were to do, and that's a very simple QP. If you were to run something like a particle swarm optimization on a radiation hardened processor, it can take anywhere between 30 seconds and 5 minutes. So that's current state of the art in terms of implementing an algorithm on a processor. But the other side of the coin of not only just how do we build our algorithms more efficiently is how do we build better processors. And that's another open topic that's being explored out here that I don't think I have time to speak to. But I'm willing to follow up with if there's more questions on that.
So how is the rendezvous done currently? So that it sounds like they're not using MPC right now on the satellite for doing a rendezvous. What's the state of practice for that?
Well, so with the state of practice right now, there's really not a lot of rendezvous missions very up close, Stanley. The last current mission from AFRL was the mission called Eagle Mycroft, which just ended about a year ago. And a lot of those operations were not fairly close. So a lot of the planning was done on the ground, actually using an optimization policy, but not enacted in an MPC fashion. It was just an optimized path, and then the waypoints that were generated were uploaded to the vehicle every day. But there was nothing aggressive about that mission, and so it didn't require MPC. But that's not to say that we're going to not need it for the future, especially as we start looking at some of the other missions. If you start looking at NASA's Restore L mission or the OSAM mission, which look at, or DARPA's OSAM mission, which start looking at in-space logistics, that feedback loop has to be closed a little bit quicker. But those missions are baseline to launch in the next couple of years. So I can't really speak to those computational methods right now, or those
I see. So it's really like you get new capabilities if you could do this on a satellite.
Oh, exactly. And I mean, I think there's a lot to be gained, not only just from just a standard formulation of MPC, but just enacting it on board in general can lead to a variety of different aspects, especially if we're starting to really play with the idea of multiple satellites around one another. The aspect of safety and optimality is really going to be critical. I'll take a feasible safe path over optimality any day, but if you can give me optimality via MPC, that's even better. Anything else?
I guess I have a question, Grace. The state-of-the-art processor is this BAE, 200 megahertz clock system, right? If there was to be a proposal for a new processor, what are the hoops that one needs to jump through to get it on space? Or CubeSats allowed to do some kind of testing already and it's more flexible?
Yeah, so for CubeSats, if you design a processor and you really want to get it up there, I mean, there's already been CubeSats that have launched Raspberry Pis on there, and that's not difficult. As long as you have a as long as you have a policy document to how you want to design your spacecraft and deorbit your spacecraft, getting a processor up there is not hard. The problem in the space community actually is more so of people really stuck in their ways. They really think that, well, we've done this for 20 plus years using this processor. Why do we need something else? And so really the hindrance is not getting something on orbit, because we can simply do that with the ISS. And that's a pretty rapid turnaround. But it's convincing people to put a new processor on board and promise them that it won't ruin their other satellite mission is the big thing. The space community is very risk adverse. So even enacting an MPC policy would scare about 90% of the space community, because they don't want the satellite they don't want the satellite being inoperable. That's about several $1 million out the window. So the hoops to really get something on orbit is really to demonstrate, yes, this algorithm or this processor is safe. Yes, it won't affect the other subsystems. And even if something does break, I can recover and still operate on my primary mission. Does that answer your question, Ricardo?
Yeah. So we are ready for our next slot. This is great. I love going over. I like discussions.